Okay, I think we got a pretty good crowd here already, so I think we're about ready to get started. So good morning, everybody. My name is Kelly Torrey, and today we have the pleasure of hosting Brandon Schwartz from Penn State for our Bureau Seminar Series. Today is February 18th, 2022. And today Brandon's going to be giving a talk on his work in hydrogen storage, which is a really important topic right now, so we're really excited for this talk. As a reminder, before we get started, for everybody, please hold your questions until the end so that we can keep everything on task. And if you'd like to type your questions into the chat box so that you don't forget them during the talk, then you're welcome to do that, or you can ask your questions at the end. And as a reminder to those of you who will not make it all the way to the end of this talk, next week, our speaker will be Kyle Henderson from McGill University, and he'll be giving a talk on lithium and smackover brines. So let's talk about Brandon. Brandon Schwartz is currently an assistant research professor in the Department of Energy and Mineral Engineering at Penn State University with expertise in the areas of experimental geomechanics and dynamic rock physics modeling. His interests are in characterizing the deformation-driven impacts of fluid injection, flow, and storage on rock and fluid properties with application to carbon sequestration, induced seismicity, nuclear waste disposal, unconventional reservoirs, and underground hydrogen storage. So Brandon, thanks again for coming today, and I'll turn it over to you and take it away.
Thank you so much, Kelly. And it's great to be here remotely, of course. Hopefully in the future, I have an opportunity to be in Austin. That'd be great. But this opportunity came about because of a presentation that I gave at the Solution Mining Research Institute, I believe, in Galveston in September, and met Lorena, which was fantastic, and just began talking about this space. And it is a very interesting space. I think hydrogen storage is one of those areas where we're currently borrowing a lot of research from utilities storage, from carbon sequestration where applicable, but it's a brand new space. We all know the direction that the energy grid is going and the role that hydrogen can play, especially because it's dispatchable, and how that could mean that it could be used to smooth out intermittent sources of energy generation. So the talk is called Techno-Economic Analysis of Enhanced Performance of large-scale wind power generation using underground hydrogen storage. So real quick, just to talk through what we're planning to cover today. Techno-economic analysis is kind of a bit of a buzzword for those of you that aren't in that space. It's come to mean a lot of different things. You'll see it on a lot of papers that cover a lot of different aspects of techno-economic analysis. But in this case, what I specifically mean is we're going to look at how we can integrate one technology into an existing technology and how we could then enhance the performance of that existing technology, in this case, wind power generation, using a new technology, in this case, hydrogen storage, particularly in salt caverns, although you could certainly store it in other types of geologic media if you wanted to. And so what we're looking at is large-scale power generation. Right now, wind energy is kind of limited in its ability to take over large portions of the electricity grid, just because the more your electricity grid relies on wind power generation, the more important these issues of unpredictability or intermittent wind velocity, et cetera, come into play. So that's what we're looking at. Can we create a situation where wind power generation has a better economic return by storing energy beneath the farm, or beneath the project, in a way that creates a dispatchable energy source? So first things first, the results. And so we looked at a 1 gigawatt nameplate capacity wind project, which had, I think, 500 2 megawatt nameplate capacity wind turbines. And so the way that we're measuring increased performance in this case is by increasing the capacity factor. So for a wind turbine, usually you have its power output, which, nameplate in this case is 2 megawatts, but you also have its capacity factor. And so its actual output on a weekly basis or a daily basis or a monthly basis is its capacity factor times its nameplate capacity. So it's if a wind turbine has a 50% capacity factor, and it's got a 1 megawatt nameplate capacity, then you'd expect that it would be putting out 50% of that, over the course of time. And so we'll show you how we got to the conclusion that we were able to increase the capacity factor by 24% by storing hydrogen underneath the project. But in particular, because this is a 1 gigawatt farm, that's 168 gigawatt hours nameplate capacity of electricity generation. So it comes out to 41 gigawatt hours of additional utilization. And so we looked at 1,056 different combinations of project variables. We've got, I think, 10 variables that we're looking at. And so in the base case, we're looking at no storage. If you just have a regular wind project of 1 gigawatt size, then what would the rate of return be? And so that rate of return ranged between 8% to 20%, which is typical of these projects. And so on the lower end, you look for better financing, or perhaps you need more subsidies. And on the higher end, there are certainly wind projects that have a natural 20% rate of return. But then we also saw, in my head slightly obscuring the words, with storage, we saw that rate of return, which is the main way that we're using to measure increased economic performance, that the ROR jumped to between 20% to 35%, in general. And so you see this tremendous increase in rate of return. So the left-hand side is showing these 1,000 plus scenarios that we ran. And you see there's 3 different capacity factors listed. You've got a 26% capacity factor, which is just a few scenarios looking at that. That would be a no storage situation. And then you see this 50% capacity factor and 74%. And importantly, in this case, what we mean to say is we're increasing capacity factor without losing power generation. So there's typically this inverse relationship between, you can have a high capacity factor for a wind project, but it comes at the cost of power generation. So it's kind of like you can only get so much energy out of the wind. And so you have this trade-off between capacity factor and power generation based on for each individual turbine. But this is a way that essentially you aren't having to go through that trade-off. So you can see that some of these RORs are incredibly high. For these green dots are looking at storage scenarios where the net present value is in the billions and the rate of return is greater than 30%. So it suggests that for this space that we're all interested in of hydrogen storage, there certainly is tremendous opportunity. Of course, we'll talk towards the end about the things that would need to happen for these to take off, in particular midstream development, end users. We need to actually have a reason to use hydrogen. And once we do, then it would be expected that there's this natural profit motive inherent to these projects that would actually create the incentive for them to be pursued. So if you're not familiar with wind or intermittent renewables, then essentially they're great because they're renewable. They don't emit carbon dioxide or other greenhouse gases during generation, but they're intermittent. And so this right-hand image is showing a few different things at the same time. This dark black, is my cursor visible? The one that is my mouse moving around the screen?
No, you'll have to change it on the laser pointer.
How do I?
You right click on the slide.
Oh, because I'm sharing my screen the way I am, I can't. Let me do this real quick. This is not a huge deal. I'll just stop the share. I will reshare, just basic.
Your fancy share, it doesn't recognize
it didn't work.
now, huh?
So do you see the same PowerPoint now?
Yes, it's not on presenter mode yet, but yes.
Okay.
There it is. Okay.
So now I have a laser pointer. Okay, great. We're right back. Okay, so what I was looking at was this bottom dark black curve is showing if you needed an average of about 1 gigawatt of power generation from wind turbines exclusively, then you're not going to get a very smooth curve. And so some days, for example, this is 168 hours, that's 1 week. For these 2 days shown here with these big peaks, you're generating a lot more electricity than you actually need. And so that consumption is this kind of dotted blue line. And if you look closely, then power generation is diurnal. Did I just lose my share? Or is it still sharing?
No, it stopped.
Let me try again. See if we can fix that. Is it sharing again?
Yes, it is.
Okay. Pointer options. laser pointer. So if you look at the demand curve, they typically are diurnal. We use more electricity at night when the sun goes down. We also use more energy when it's colder out. So you see some, this is a standard consumption pattern in this case for something that like a 2 gigawatt small city or something like that. So the point is there's this mismatch, usually with conventional, with fossil fuel power plants, for example, or nuclear. We can match supply and demand very easily because we're using natural gas or coal. And if we can anticipate an increase in demand, we just create the increase in supply. But with wind power, we can't create more wind. And so if the wind is blowing, we get electricity. If the wind is not blowing, we don't get electricity. So this mismatch is the standard problem with renewables. But what you could do is if you've got this difference between demand and supply, then when you have these days where the wind is blowing very strong, where you're able to generate more electricity, you could store that excess, in this case, using water electrolysis. You pass a current through water, it separates the H2O into oxygen molecules and H2. And so you can take gaseous hydrogen and you can store it somewhere, either a surface container, or you can store it in the ground in like a salt cavern or something like that. And then for these moments where you have a shortage of wind power generation, you could then dispatch that hydrogen to make up the difference. And so it's a sort of way to smooth out this mismatch between supply and demand. And so you're talking basically some form of battery storage. And so with renewables, we all know that battery storage would solve the problem. One of the issues with these large scale projects is you would need a lot of batteries for chemical batteries. And so things like pumped hydro would work if you've got the right setup, or a salt cavern would also work, some type of subsurface storage, in this case of hydrogen. So we all know that it would work. And so this left-hand image is from Cortagino 2016. It shows kind of the setup that you've got a wind turbine that's generating electricity that goes towards the grid. But if there's an excess, then you electrolyze water that creates oxygen molecules that you emit, but then you store the hydrogen, in this case, in these salt caverns. They're kind of pill shaped. If you've got enough salt available, you don't have to store it in salt caverns. You can store it just in the ground, but salt caverns have the best efficiency. And then when you need to dispatch it, you could put it into the electricity grid, or you could use it to power vehicles or as industrial feedstock, et cetera. So we know that this works. This is the idea. Of course, when you combust hydrogen, it turns back into water. And so you have this closed loop, which makes it renewable, which is pretty interesting. And so that's an example of green hydrogen, where you're not getting it from a fossil fuel, you're getting it from water, and then it returns to water when you use it. And so you've got this renewable closed loop. And we can use it for all these different aspects of energy consumption, which is what underpins this concept known as the hydrogen economy, or what's lately been called the new hydrogen economy, where we're looking at different ways that we could really incorporate hydrogen into what we're already doing. So we know that this works, but what we wanted to do is we wanted to quantify how good is it, or how would the economics of our current grid improve if we actually had hydrogen storage. And so to do that, we looked at some actual consumption patterns and wind power generation patterns from PJM in the Northeast, which is a large, essentially, utility provider that has a lot of publicly available information. And we took these two curves, supply and demand. We looked at the natural mismatch, and we figured out, well, how could you anticipate storing hydrogen through electrolysis at these periods where there's a surplus of power generation, and then how could you dispatch it? And then if you could do that, what would the increase in the project economics be? So that's essentially what we are looking at. That's the setup here. So getting into the model assumptions real quick, we are assuming a cavern depth of 1,000 meters, which is sort of standard. The deeper your cavern is, the higher your pore pressure or your internal cavern pressure could be. We're assuming about a 500,000 cubic meter storage volume of hydrogen. The operating pressure would be between 60 and 180 bar, or 6 to 18 megapascals, or 900 to 2600 psi, which is a decent range. And a salt cavern could handle that change in effective stress. I will mention ahead of time, we're not imagining a scenario where we're creating and dispatching hydrogen daily. You would be charging the cavern throughout the course of a month, and then it would be dispatched probably once a month to some type of midstream network. The storage capacity, if you look at the storage volume, 500,000 cubic meters, and then you look at hydrogen as a molecule, would be about 140 gigawatt hours of thermal energy, or 85 gigawatt hours electrical. And so that, if you're familiar with hydrolysis, you're looking at about a 60% efficiency in conversion. 60% is a bit high, 40%, 50% might be a little bit more realistic, but this is just, we got all these numbers from the literature. And so we noticed that it was 60% efficiency, which is high, but not unreasonable. You'll also notice that because this is a 1 gigawatt wind farm, so 168 gigawatt hour nameplate capacity, 85 gigawatt hours would cover about 3.5 days of electricity needs. The maximum flow rate that the cavern could handle would be 11,000 kilograms per hour. We're actually looking at something closer to 8,200 kilograms per hour. I will point out that if you look at the expected flow rate and the electrolysis costs, we are assuming electrolysis cost of $2.30 per kilogram. And if you do 8,200 kilograms per hour over the course of a year, then it comes out to $168 million per year for electrolysis costs. Again, this is a 500 wind turbine project. That is, each of these turbines are 2 megawatts. So you get 1 gigawatt total nameplate capacity. And then looking at the cost of turbines and installation, you're on the low end, you could do this for $1.3 billion, and on the high end, it would cost $2.2 billion. And so the difference in CAPEX in this case would be the cost of steel, how close you are to your raw materials, how spread apart does this project need to be in order to capture differences in wind patterns, et cetera. We're assuming that there's 200 miles between the project, or that we need a total of 200 miles of transmission capacity just to get the electricity to market, wherever that would be. And then we're also assuming compression costs if we need to get hydrogen into a pipeline of about $4 million per year. And so you can see through these model assumptions that we're developing some upfront costs and some annual operating costs. And so the way we looked at it is, if an engineering firm were hired by a utility company for a consulting project to actually build out this model, this is how they would approach it. They'd create CAPEX, OPEX. They would look at cash flows over the course of, in this case, this is a 40-year project that we're assuming, and then they'd provide the results. So a quick table for you. So again, we're going to look at two situations. One where we have this ability to store hydrogen, and we have a lot of different variables that we want to sample over just to get a sense for what the range of outcomes would be. And then we're also going to look at some where there is no storage. So just if you were to model a 1 gigawatt, nameplate capacity wind project without any storage, then what would its rate of return be? And so to do this, we wanted to pick a high and a low so that we could do a bit of a global sensitivity analysis. And so we've got these, I think, 10 variables that we looked at the literature pretty close, and we've got our references are shown in the rightmost column. And so one thing we're looking at is corporate tax rate, ranges between 21% and 31% for a blended rate. The cost of electrolysis, we have a high from the Department of Energy of $3.10 per kilogram, but we also have this assumption of zero. We'll talk about that more in a minute, but essentially what we're doing here, or we're assuming that electrolysis would cost zero, is in the literature for the economics of wind power generation, you see this assumption a lot of times. What is the value of electricity generation that doesn't get used? If you generate a megawatt hour of electricity, but it doesn't go to use, then what is its value? And it is usually priced at being worth nothing because it's not used. Or maybe more specifically, if you have over the course of a week, if you have a lot of wind power that goes unused, then it very quickly the price goes down to zero. And so what we're looking at is if the economic models are giving this excess power generation zero value, then that would mean it would also have zero cost if we were to use it for electrolysis. And so we're kind of sticking to this idea for sake of conversation. In reality, what would happen is that this excess power generation would then be passed through water, and then that water would generate hydrogen. And then we've got compression costs and storage costs, which we've modeled, but the actual cost of electrolysis itself would in fact physically be zero, because you're using this, you're using what would otherwise be a worthless packet of electricity to do something useful with it. We've got compression and storage costs listed in dollars per kilogram in our model. We've got the production tax credit for wind turbine installation. The PTC has been very successful in getting the wind industry off of the ground. And so it's we created a range for that because we wanted to see what impact the production tax credit has on these projects. And then we also wanted to compare it to what impact the storage has. So we're comparing the production tax credit to just hydrogen storage without a subsidy. And we'll talk about that in a moment. We looked at the capacity factor for these 2 megawatt wind turbines. And so a University of Michigan study just 2 years ago put out some information on that. We've got some transmission costs. We've got the CAPEX of the wind turbines themselves, the cost of the electrolyzer, which would be an upfront cost predominantly in millions, cost for compressors, compressor stations, storage costs, which is largely the salt cavern, developing it and then maintaining it, et cetera. And so that's all of the assumptions and the places in the literature where we get those assumptions for the storage scenarios. For the no storage scenarios, the main difference is all of these costs that you would have with hydrogen storage, you are foregoing those costs. So the project has less CAPEX and less OPEX, but then the question is, does the benefit of storage outweigh the additional costs? You may notice that the electrolysis costs are zero. There's no cost to compress hydrogen. The production tax credit is the same. The capacity factor is now dropped by 24%. And we'll show you where we got that information on the next slide. But this is the scenarios where there is no storage. It's just a bread and butter wind project. So as far as increased capacity factor, if you didn't need to forego power generation, and you could have the same power generation at the same capacity factor or at an improved capacity factor, we calculated this really just using Riemann sums. And so I had a student work on this with me. I should have probably put his name on this. His name is Duke Nyan. He's very good. He did very good work last summer on this part of the project. So what Duke did is he created some code that looked at these demand curves for PJM. And so what we're doing here, you'll notice that you've got January, February, and March. We took 12 months of wind power generation and electricity demand. We scaled it all to 1 gigawatt because that's what we're assuming the needs are for our hypothetical project. But to get 12 months, we didn't do January through December just because the energy uses over the course of a year in any local area just fluctuate seasonally. So what we did is we took January, February, and March, 2018, 2019, 2020, 2021. So that's how we got our 12 months. We wanted to see, because energy uses are pretty static over those 3 months because it's winter, we just wanted to compare, have extra data, in this case, 12 months worth of data, and look at, and they're all different. We're just showing the ones for 2021. And then we wanted to take all of these months and look at these overages and shortages. So you'll recall, in this case, the demand is greater than the supply. And so that would create a situation where there's a shortage. You would need to have hydrogen dispatch in that case. Towards the x-axis is in hours. This is 168 hours, which is 1 standard week. We're looking at power generation between 0 and 2.5 gigawatts on the y-axis. And so if you were to look at these sections of this plot that are where you've got the blue curve is beneath the supply curves, that is where demand is less for that part of the week than the wind power is actually generating. This area towards the bottom right, this is where you'd actually have electrolysis happening. That's creating hydrogen that can then be stored, and then in theory, that same storage is used to smooth out the fluctuation where you've got an energy shortage with wind power. And so, if you do this match, if you can anticipate when you need to store hydrogen versus when you need to dispatch it. Or if you've got over the course of 12 months, this cavern is sending hydrogen to a midstream network for distribution, and you can then use a dispatchable commodity, in this case, hydrogen gas, to meet all of your electricity and energy, other energy needs, then you've got this, now you've got a match between the supply and demand. So that's what this right-hand side graph is showing, is when you'd be dispatching. And so it's kind of like the opposite. You'd be dispatching towards the end of the week, like we mentioned, and you'd be storing on the other side of the week. So to get this increased capacity factor, we look at these 12 months, and so you'll see them here: January, February, March 2018, January, February, March 2019, January, February, March 2020, January, February, March 2021. And we looked at, if you were to then utilize this hydrogen, for electricity needs in this case, then for each of those individual months, what would your increased use be? And so in this case, you've got 168 gigawatt hours being nameplate capacity available per week. How many extra gigawatt hours are we able to get out of this project, assuming that we're able to dispatch hydrogen? And so you see that the fluctuation is essentially between an increase in capacity factor of 21.5% all the way up to 25.7%. But then it's not a very wide range, which is useful, because essentially the average is 24% and the variance is not very high at all. So you're looking at, essentially, in this case, with our assumptions, you're getting about 24% more generation capacity available to you that you can then dispatch for electricity generation. So the next thing we did is we've got these 10 variables that we're looking at. We know that the capacity factor increases by 24%. So this is where we get this difference in capacity factor. I'll point out where on this slide capacity factor is. This is where we get from the base case of 26% capacity factor for the low and 50% for the high. Without storage, this is how we get to a new capacity factor of 50% to 74%. But what we do is we took all of these variables that we worked over the summer to capture the highs and the lows for, and we put them into a model, a cash flow model, where we've got, for year 0, we're assuming all of our costs are upfront, even though they probably occur over the course of a few years. We're assuming all of these costs are occurring at time 0, and then we've got annual cash flows, where we've got costs subtracted from cash inflows, and we've got a number at the end. Some of these numbers are negative. Some of these projects, you lose money every year. But for the ones that have a positive cash flow for every year of these 40 years, we then calculated the rate of return. So like we said, we've got the tax rate, corporate tax rate, the cost of electrolysis, where it's either 168 million or it's 0, depending on your philosophy, cost to distribute the hydrogen, what is the value of the production tax credit, transmission costs. The CAPEX is largely driven by the cost to install these 500 2-megawatt turbines, the cost to install the electrolyzer, and then the storage costs plus compression. So what we've got is we're picking a high and a low. So if you do every possible combination, if you assume that every one of these variables is independent from the other, and we want to look at all the possible combinations, you've got 2 to the 10 possible combinations, which is where we get our 1,056 possible scenarios that we're looking at. And so when you look at all of these together, you have a decent sense for, how each individual variable is influencing the rate of return independent of the rest. And so we used GAMS to do this. You don't need to use GAMS because we've got 40 years and we're assuming 40 compounding periods. And we're assuming that all of the CAPEX is up front at time 0 with no financing, by the way. You could just do, there's a good trick. If you've got more than 10 compounding periods, then you can just do the annual cash flow divided by the CAPEX would give you the rate of return. But we did it both ways. So we used GAMS to actually interpolate and discover what is the rate of return for each of these cash flow diagrams. But then we also did the quick and dirty way. And there's a pretty good match. And so as far as the rates of return, we're looking at some histograms here. On the right-hand side, you're just looking at the 32 scenarios that we looked at that didn't have any storage. And you're also looking at the 1,024 scenarios, 2 to the 10, the scenarios that had storage. And so we've got these buckets for internal rate of return on the x-axis, and then this should say total percentage of scenarios, not total number of scenarios, excuse me. And so then we've got these smoothed out distributions. And so what you're seeing is that the mean for the no storage scenarios is somewhere around 10-11%, which is actually what you see in the wind industry. That's not surprising. Even if you've got, in this case, you're looking at a scenario where you've got a really good CAPEX, the price of steel is low, the distance between your manufacturing and your project is not very large, et cetera. But you do have quite a bit of variability. But then with these storage scenarios, you'll see that the average or the mean is somewhere closer to 20%. So what this is showing is that even though there's these increased costs with hydrogen storage, there's also this increased benefit where you're able to use this extra 41 gigawatt hours per week of some type of electricity utilization. And there's a range. I mean, in both cases, the range is between about 7% to 40%. But if you were to do kind of like a band filter of sorts, then we're basically saying we see that the no storage scenarios range between about 8% to 20%, although you do have some scenarios that are higher than that. Most of them are in this bracketed range between 8 and about 20%, whereas the storage scenarios are closer to perhaps 20% up to 35% is kind of what we're interpreting this as. One other thing I do want to draw your attention to is on the right-hand side, this is looking at what is the actual value of hydrogen. Hydrogen gas is a commodity. And so we're looking at $4.30 per kilogram, as well as $5.90 per kilogram. There is this big push to get the cost of hydrogen down below $2 per kilogram. And so if that ever happens, then these numbers decrease. But the main thing you're looking at here is you also have this bottom and top range of capacity factor. And so what you'd expect to see is that the absolute best case would be where you get the cost of hydrogen generation is $4.30 per kilogram with an increased capacity factor that's very good, about 74%. And then on the bottom range, you've got a higher cost to generate hydrogen, and you're only getting about a 50% capacity factor for that same 1 gigawatt nameplate capacity wind project. But all of these are looking very good. I mean, the no storage scenario is the current situation. We don't have any projects where you're using water electrolysis to generate hydrogen for dispatch later. You'll notice that this curve, it's way down here. It's not good. The average is what we showed before. It's the same blue curve that you see on the left. It's just flat because there's not very many scenarios, but it's way down here. So it's not, even if the cost of hydrogen generation is expensive, the benefits still far outweigh having no storage options available to you. I do want to look at a modified tornado plot. We're just comparing two scenarios that were typical of what we saw. And so in this case, what we're looking at is what variables had the largest impact on the net present value. So this is in millions. We had some, for the best case scenarios for hydrogen production and sales, we had net present values over $5 billion is what you're seeing here. The CAPEX had a large range as far as its influence on net present value, anywhere from, if you've got a very high CAPEX project, you could have a negative NPV of $3 billion, which would be a terrible project. You also had ranges up to about $2 billion. Electricity sales had an impact, and I don't want to go through all of these, but what I want to point out to you, the very bottom, the production tax credit. The PTC has gotten wind off the ground as far as the industry goes, but if you compare it to hydrogen production at the top, the PTC doesn't have much of an influence at all compared to the ability to capture and then later sell hydrogen, in this case through electricity sales. And so one thing that we're looking at as far as an interpretation of our results is we've got all this money being dumped into the PTC. It might be better to put that money into a subsidy for cavern development so that this hydrogen can be stored. From a policy perspective, that would actually have a larger impact on wind penetration into our grid than just subsidizing the cost to install and maintain a wind turbine. Real quick, let's look at capacity factor and CAPEX. So on the left-hand side, again, these are cross plots of NPV on the x-axis and rate of return on the y-axis. We actually saw this left plot before. there's this split that you'll notice in these values. This is 1,056 scenarios. And that split is due to some of these have a CAPEX of $1.3 billion to install these turbines, which is by far the largest portion of the capital expenditure. And then some of them have a CAPEX of 2.2 billion. So that's where the split comes from. But then all of these scenarios, for the most part, have the increased capacity factor up to 74%. Those are way up here. They've got really high NPVs and they've got really good RORs. Some of them don't. I mean, some of them are dogs. You always have your dogs. If you got really bad project variables, that would be a no-go scenario. You just would not have. You wouldn't run that project. And so anything between, I would say, 0 to 10%, you're going to have to find some really creative financing for that project to get off the ground. And again, these projects have negative NPVs, so they wouldn't be financed anyway. But what you see is that there's this split with CAPEX, and then there's this split with capacity factor. So your best projects are going to be where you're able to get the highest capacity factor using hydrogen storage, and where you also have a really good CAPEX, where the price of steel is low, where you're close to your manufacturing facilities, etc. Same thing here. What you're looking at is this is the cost of installation. So $1.35. This is per wind turbine for the project versus the blue ones, which is the cost in CAPEX for the higher end. And so what we're looking at here is this split. Some of these projects are naturally attractive, whether you have storage or not, but having the ability to store in all cases enhances the projects. As far as storage versus no storage, in this case, we've got no storage scenarios. We're looking at the NPV of the project versus the break even. And so a good break even would be something like 5 or 6 years. Some of these projects break even very early. Even with no storage, you'll see that some of these are breaking even within 4 years. Again, that's true of some wind projects, especially when you've got an area where you've got low CAPEX and a good PTC. So we're not saying that you can't have wind projects without storage. What we are saying is when you do have storage, some of these projects break even within 2 years. And so that would be an interesting thing to explore even further. So you'll notice this is more of an academic thing. This is my favorite plot for reasons that are not important. But if you cross plot the rate of return versus the break even, this is just a mathematical curiosity. It's because these are the inverse of each other. Of course, all of the 1056 scenarios collapse to one single curve, but you still do see it from an interesting perspective where you're looking at, if you've got this ROR and you've got this break even period consideration, then this is the curve that these fall on. And so some of these are very, very good projects where you've got these storage projects, where I would say in this region right here, you're looking at very good RORs, very low break-even periods, very good projects. So just for a few minutes, I want to talk about some considerations. So as we saw in the data, the cavern storage has a larger impact on the rate of return than the production tax credit. And so one thing that we're looking at is that policy should shift towards subsidizing the ability to store hydrogen. And we'll talk about that in just a few bullet points, because one of the reasons we aren't doing that is because we don't have a lot of end uses currently for hydrogen, and we also don't have any midstream abilities to send it from a storage location to a location where it would be in demand. 41 gigawatt hours is half of the electrical storage capacity of the cavern. And so one thing we were looking at is this assumption of a 500,000 cubic meter system of probably 4 or 5 salt caverns. We'd almost want that to be a little bit bigger, because withdrawing half of the gas at one time is a bit of a lot. So you'd have to have an interesting setup where you're not drawing down so strongly and creating this change in effective stress that could cause the cavern to collapse. You'd probably want a system where you're whenever you've got excess generation, you're charging your cavern for a few months, and then you're slowly dispatching it to keep the cavern stable. And with that being said, we're not dispatching directly from the cavern to a power plant. We're dispatching to this midstream distribution network. And so you're looking at probably 6 to 12 withdrawals per year, and then charging in between. One thing to look at is we're looking at a system where the same entity that's applying for financing is installing the wind turbines and the cavern, and so maybe they're also the utility company, and that's possible. So there's the built-in inherent ROR. But if you've got multiple entities that maybe you've got a utility company, and then separately you've got a wind turbine company, and then separately you've got a hydrogen storage company, and then separately you've got a midstream development company. These each need to have a positive ROR. If one of them doesn't have a profit motive, the project's not going to happen. And so we need a little bit more of a new, I think future work in this case would be to nuance between these entities and to make sure that each separate section of the project has a positive ROR that's attractive to investors. And then I think the other consideration is back to this idea of the cost of electrolysis. Again, if from an economic perspective, currently we're going to price the value of wind energy that does not get used at zero, then that does mean that the cost of electrolysis is also zero. So it's free energy. If it would otherwise go unused, then from an economic point of view, using it to induce a current, to run through water to generate hydrogen gas also has zero. So I think it's an academic point, but one that's worthwhile nonetheless. Okay, so summary, we showed that cavern storage below a wind project for 1 gigawatt nameplate capacity increases the capacity factor by 24%. So if you started off with a 50% capacity factor, then you were only getting 500 megawatt hours out of that project. This is showing you're getting that additional 41 gigawatt hours. So it'd go up to 70, what would it be? I'm trying to think, 740 megawatt hours of electricity utilization. We looked at no cost scenarios. We also looked at scenarios where are no storage scenarios as well as storage scenarios. And we found that on average or over the course of multiple scenarios, you've got this typical range where the storage without storage, wind projects range between 8% to 20% for ROR. And we already know that. But then with storage, it enhances these projects and the RORs are much more attractive. Again, this is assuming you have a place to sell the hydrogen or you have a way to utilize it when it's needed. And that's what's missing right now is we don't actually have a use for hydrogen. We just assume that there will be a future use for it. With this setup, this also means that wind power could be used as kind of like baseload power, kind of like hydro or nuclear are today, just because you've created a dispatchable power source within the overall project. And so you're flattening out this difference, this mismatch between supply and demand. We also think that future work should include interbedded salts because you only have really thick salt deposits in some parts of the world. And so interbedded salts are a bit more common, but also hard rock caverns would also be useful. We have no research really at all on the interaction of hydrogen with hard rock caverns and all these various pathologies that you would come across. The CAPEX is about twice, we know that. So your RORs are going to decrease substantially, but if you're starting out with a 40% ROR with salt cavern storage, that would be a 22-23% ROR with hard rock caverns. So it's still a very good project. So this is where we think the future work needs to go in order to expand our knowledge in this space so that when there is an end use for hydrogen, we're ready. So thank you so much for listening. I appreciate it very much. And at this time, I'll certainly take any questions.
Thanks a bunch, Brandon. That was a really interesting talk and a really cool way to look at the economics of and the actual feasibility of being able to really utilize hydrogen storage effectively going forward. So thanks a bunch for that. And we'll start with the questions. I saw quite a few questions have been popping up in the chat. So Linda was the first to ask. Linda, do you want to unmute to ask a question? Or do you want me to just read? Oh, here you are.
Brandon, thank you. What a cool analysis. I really enjoyed your talk. We're in this scenario now where we're looking at potentially having rising interest rates, and just wondering if you did sensitivity when you have the net present values, what was the interest rate that you used, and did you do sensitivity on if it rises on feasibility?
So we did not do a sensitivity analysis on that. We assumed a 10% hurdle rate for the MPV. So we actually, I forgot to mention, we're hoping to submit this work to a special issue of Geological Society of London within a few weeks. And we're hoping to actually have that finished by then. so hopefully we can share that manuscript with you. But that's a very interesting point. We did do some playing around. I always assume 10% hurdle rate. I don't know. I was taught that. We did look at other hurdle rates, and you do get very different NPVs, certainly. So to your point, it's a very important consideration.
Thank you.
Okay, the next question was from Ning Lin. Ning, did you want to unmute, or do you want me to just ask for you? There you are.
Sure, I can ask Brandon, thank you so much for the presentation. Very interesting. I have actually, I wrote 2 questions. And so if you don't mind, Kelly, I'll just ask one together.
Yeah, go ahead and ask both.
One of them is, it's quite interesting of the increase. It's obviously a very attractive project if we could increase MPP that much. But I wonder that because you assume a 1 gigawatt wind generation, that's a pretty large capacity. So have you looked into a smaller capacity, whether you would get a similar result? Or, I mean, probably shrink, but I'm kind of curious if there is a threshold. The size has to be a certain size for this to work.
I've not looked into that, and it's a very interesting point. I mean, so with these larger projects, you get the benefit of wholesale cost reduction, but then you're generating less hydrogen, and so I don't think it would be just a straight line, scale up or scale down. That's worth looking into. I agree with that.
Yeah, and also another question would be, I didn't quite, probably I missed that, but for the market that you're talking about $3 or $4 per kg of hydrogen, are you assuming, is that like you're selling this as hydrogen as commodity, right? Not
yeah.
So that I assume that would be a market or local demand pretty close to your site. Otherwise, it would have some type of transportation cost.
So 2 things. First up, because this is being recorded, I think I misspoke on that slide. And so anybody that wants to go check, I didn't mean that was the price to sell hydrogen. That's the cost to generate it, is what we were looking at. So I misspoke with that. But as far as the cost to get to market, we did have compression costs. We're assuming a certain transmission capacity of 200 miles of between us and the market. But that actually is the next thing we want to look at, is we didn't really, our analysis kind of ends at dispatch. We don't consider the midstream market at all. And you're absolutely correct. And that completely changes, the attractiveness of the project. So no, those are certainly interesting considerations as far as what's the cost to generate hydrogen, and then what price would you get if you were to sell it as a commodity. We assumed we were using it for electricity generation, which kind of made it more of a simplified analysis and a little bit more specific to just that. But even then, we were, I think, considering using it essentially like a natural gas feedstock to a power plant. And so the price we're getting is whatever the cost of electricity generation is, whatever that can be sold onto the grid for.
It's just one thing add to that. I was wondering if you're looking at a RGGI state, like a state which with CO2 credits or something like that, if it's you're really subsidized for a gas fire generation, maybe this will give you extra incentive for hydrogen. I don't know.
Yeah.
But since you're talking about PJMs, I was thinking about RGGI state.
Yeah, absolutely. No, I was asked that same question in Galveston, and it struck me as that's absolutely true. So if you're able to forego carbon dioxide emissions, then you do get a credit. We didn't look at that, but we should. We absolutely should. Somebody's getting that credit. So this is an added incentive. Even with these high RORs, somebody has this added incentive of a tax credit. So you're absolutely right.
Yeah, I definitely think that if you're submitted to for Europe, their credit, I know as a fact that fire generators are getting charged, only electric fire generations really get charged by a carbon price, but I'm not sure about PJM personally.
Okay.
So, but that would be a really I'd probably give more benefits for the project.
Yeah, definitely. Thank you.
Thank you. Very interesting.
Thanks, Ning. Our next question is from Peter Eichabel. Peter, did you want to unmute?
Yes, Brandon, interesting talk. You only consider hydrogen generation as the only storage technology. But if you go to very short fluctuation supply demand, battery storage would be probably more economic, right? So if you're talking about hourly to daily variations, right? Then the hydrogen generation would not be cost competitive. So I wonder if you had both in conjunction, battery storage for short term and then hydrogen for more longer term, how would that affect your calculations?
That's such a great question. I'm writing a sticky note that I need to write a paper on that. That's a really great point. So I don't know the answer to that. Maybe you might have more insight. What do you think?
Well, I mean, there's also, and I think that relates to the first question you got from Linda, is there's the cost of capital, right? So if the hydrolyzer plant is sitting idle, it actually costs you money because an idle plant is not producing is a loss in revenue, right? So if you have another technology that fills that gap, it could even be more economic, right? So it could actually work in your favor, right?
Yeah. No, I completely agree. I'm interested, even aside from hydrogen, in just this concept of a really robust smart grid where we've got so many batteries in our daily lives that they could be used individually to meet these demands, even though they might not be connected directly to the need. They're around and they've all got a computer in them, and they could all be technically programmed to do that, which would kind of make this idea we don't need a really big hydrogen battery. We don't even need a field of batteries. We just need to have the million batteries that are already in American appliances and vehicles connected. That would actually work too.
All those cars being electric cars that are connected to the grid, right? And that could
absolutely
be both receiving power, but also supplying power to the grid, right?
Yes, absolutely. I agree. It's a very cool idea, I think.
Right. Thanks.
Very good. Our next question is from Sonia. Sonia, did you want to unmute?
Hi, thank you for the presentation. No, you answered the question with, because it's in the same line with the Ning Ling, it's the same.
Yep.
Thank you.
Yeah, she was asking about sensitivity with a wind farm of 500 megawatts or less, and you did answer that question. So
yes, because a wind farm for 1 gigabyte to energy, it's very high. You require a lot of wind turbines.
Absolutely. Now, I will add that one thing that the literature does explore, because the intermittency and unpredictability of wind, it creates a problem, especially when those 500 turbines are very close together, because whatever the unpredictability is of that field or that region, it's going to be exacerbated. Excuse me. But if you've got geographical diversity, where in this case we could talk practically 100 of those turbines are here, 100 of them are 200 miles away, then you get the benefit of essentially just a more diverse wind profile. And so whereas we're talking very specifically about using hydrogen to smooth out this fluctuation, there's lots of good studies that show that when you've got this large scale, another great way is just don't have them all in the same place, and then they can kind of buy and share from each other, in the exact same way. So that's actually what PJM does a lot of times, is they'll have buying and sharing between different states to manage the fluctuations of intermittence. So
yes, one question. Sorry, do you consider in this case that you storage the excess of hydrogen that you have, or the excess of electricity, and then you convert to hydrogen, and then this is that you storage in the underground?
Yeah.
Yes? Okay.
And that's where the 60% efficiency comes in. So it's not, I mean, if you were to electrolyze water using a megawatt of a megawatt hour of electricity, and then store it and then reconvert it to electricity through combustion, then only about 60% of that actually could be used. In fact, probably less. 60% is kind of it's a bit high. I would say between 40 and 50%. And so that 1 megawatt hour actually turns into more like 40% of that at the end used for electricity generation. So yeah.
Okay, thank you.
Okay, and our last question comes from Brody. Brody, did you want to unmute to ask that question? Or?
Sure, and Brandon, thank you very much for the presentation. Especially from a Texas perspective, where a lot of these conditions exist. This is really interesting to think about. You addressed most of the question responding to Ning, but since you don't have a midstream infrastructure that's currently in existence, and you're either having to build out or use trucks, did you consider anything, especially with your CAPEX analysis, of co-locating that hydrogen generation, power generation on site where the caverns are, especially since if you're doing that in conjunction with a wind farm, you already have a fairly robust grid connection that you can connect to, and you're not having to build that as well. So just wonder what you thought about with co-location rather than having to build a midstream infrastructure.
Yeah, no, I mean, this was a thing that we were looking at, and we essentially ran out of time for what we were looking to do. It's the next thing that we need to do is, is there a midstream development? We definitely look at, we had a separate but related project on land use. We like wind turbines just because you can farm up to the base of them. So you've got dual use. But then if you're able to have these caverns directly below, now it's like 3 uses for that same bit of land, which is useful if it can be done. And then the last piece, I think, if I understood your question, is as long as you're close to the market, then the distribution shouldn't be very expensive. But that's kind of the missing piece right now. That's what we want to look at next.
Great, thank you.
Okay, well, I think that we are about out of time and we're out of questions. So thanks again, Brandon, for a really interesting talk. We really enjoyed having you here. And I share Lorena's sentiment that hopefully next time it is a 3-dimensional visit.
Yes, exactly. Thank you all so much. I really appreciate it.
Yes. And just as a reminder to everybody else who stuck with us through the end, next week, you can join us for the next seminar on February 25th. It'll be Kyle Henderson speaking about his work in lithium brines and the smackover. So with that, thank you everybody for sticking around and for watching this awesome talk. Cheers.